Greenland looks almost featureless from space. A white ice sheet covers most of the island, hiding the land beneath more than a kilometer of ice in many places, but scientists have now reconstructed that buried landscape in much greater detail, and what they found looks nothing like a smooth frozen basin. Beneath the ice is a vast network of valleys, ridges, mountains, and channels that record a world Greenland had before it became one of the largest ice-covered regions on Earth. The new map comes from a study published in Geophysical Research Letters. Instead of relying only on aircraft flying radar lines across Greenland, the researchers used a technique called ice flow perturbation analysis. The basic idea is surprisingly intuitive. Ice flowing over a buried hill or valley does not remain perfectly smooth at the surface. The hidden terrain subtly bends, stretches, and redirects the ice above it. If scientists can measure those small surface patterns precisely enough, they can work backward and infer what lies underneath. It is a little like placing a thick blanket over a table covered with objects. You may not be able to see the objects directly, but the shape of the blanket still carries information about what is underneath. Greenland's ice sheet is vastly thicker and more complicated, but the same principle applies. The researchers combined high-resolution observations of the ice surface with known ice thickness measurements, then used the physics of ice flow to reconstruct the hidden topography between direct radar observations. The accompanying dataset describes the result as a new subglacial topography derived using ice flow perturbation analysis adapted specifically for Greenland. What emerged was not one giant canyon or a single dramatic mountain range. It was a continent-scale drainage system. Across large parts of Greenland, valleys branch into one another in patterns resembling river networks on exposed land. Some cut through regions that had previously appeared relatively featureless on older maps because measurements were too sparse to resolve them. These valleys matter because many of them may be extremely old. Greenland was not always buried beneath its modern ice sheet. Before large-scale glaciation, rivers flowed across its surface, carving valleys through exposed rock. Some of those landscapes were later covered rather than completely erased when the ice sheet expanded. Earlier studies have already found ancient river systems beneath individual Greenland glaciers, including valleys with the V-shaped profiles typically produced by flowing water rather than the broader U-shaped valleys associated with glacial erosion. One of the most striking examples lies beneath Jakobsham Glacier. Previous radar work showed an ancient drainage network there that predates Greenland's modern ice sheet by millions of years. Some buried channels were more than 11 kilometers wide and roughly 1.3 kilometers deep. Their shape suggested that rivers spent enormous amounts of time cutting through Greenland's hard bedrock before ice eventually covered the terrain. The new mapping effort extends that type of view much more broadly. Instead of isolated valleys detected along radar flight paths, scientists can now see how many features connect across the interior. That allows them to begin reconstructing Greenland as a landscape rather than merely as a block of ice sitting on an uncertain bed. And that hidden landscape directly affects the ice above it. A glacier does not simply slide downhill according to surface slope. The shape of the bed controls where ice is squeezed, where it can accelerate, and where friction resists movement. A deep valley can funnel ice toward the coast, while a ridge may slow or redirect it. Narrow troughs can concentrate flow much like a river channel concentrates water. Earlier Greenland observations have already shown faster ice flow above some large buried valleys. This becomes especially important near Greenland's outlet glaciers, the fast-moving corridors that transport ice from the interior toward the ocean. If a glacier retreats into a deep inland valley, the shape of that valley can influence whether the retreat slows or continues. A bed that becomes deeper inland can sometimes make a glacier more vulnerable because thicker ice reaches farther below sea level, allowing ocean-driven melting and dynamic retreat to continue. So a better map of the bed is not simply a geological curiosity, it can change calculations of how Greenland responds to warming. Greenland contains enough ice to raise global sea level by several meters if it were ever completely lost. That will not happen suddenly, but even partial changes matter for coastlines around the world. Scientists therefore use large numerical models to simulate how the ice sheet may evolve over decades, centuries, and longer periods. Those models need an accurate description of the ground beneath the ice. Imagine trying to predict the path of water flowing across a landscape while knowing only the general elevation but not the locations of valleys and ridges. Small errors in topography could send water in completely different directions. Ice behaves more slowly, but the same problem exists. Until now, one of the main limitations has been coverage. Ice-penetrating radar has revolutionized Greenland science. Aircraft transmit radio waves through the ice and measure reflections from the bed below. Over decades, these surveys have produced enormous amounts of information. But Greenland is huge. Radar aircraft fly along lines rather than scanning every square meter. Between those lines, researchers must interpolate what the terrain probably looks like. If flight lines are tens of kilometers apart, a narrow valley can simply disappear from the reconstructed map. The new method helps fill those gaps by extracting additional information from the ice surface itself. Features at the bed create perturbations in flowing ice, and satellites can measure the surface continuously across enormous regions. In effect, researchers are using the ice sheet as a sensor for the hidden land beneath it. That does not mean every hill and valley on the new map has been directly observed. Ice flow perturbation analysis is an inversion method. Scientists begin with what they can see at the surface and use physical relationships to infer the bed below. Direct radar data remain essential for anchoring and testing the reconstruction, but the value of the technique is that it can reveal patterns radar surveys alone may miss. The hidden valleys also preserve information about Greenland's geological past. Their directions can reflect differences in bedrock, fractures, tectonic structures, and ancient drainage systems. Researchers have previously shown that geophysical measurements beneath Greenland reveal multiple geological provinces hidden under the ice. The newly resolved valley network may allow scientists to distinguish some of those regions more clearly through the way erosion shaped them. This is important because Greenland is not one uniform slab of rock. Different regions formed at different times and underwent different geological histories. Some rock is extremely old continental crust. Other zones record later tectonic activity. Valleys often exploit weaknesses in rock, so their patterns can reveal boundaries that are invisible from above. The ice may therefore be hiding not only a lost landscape, but a geological map. There is also a deeper question. How much of this landscape was created by glaciers, and how much existed before the ice arrived? Glaciers are powerful agents of erosion. As ice moves, rock fragments frozen into its base can grind the bed beneath it. Over long periods, glaciers widen valleys, deepen basins, and reshape entire mountain systems. But Greenland contains evidence that some landscapes beneath the central ice sheet have experienced surprisingly little erosion. Sediment recovered from beneath kilometers of ice has shown that ancient soils and tundra surfaces survived for immense periods. NASA-supported research previously found organic soil beneath the Greenland ice sheet that had remained preserved for millions of years. That means the ice sheet has not acted everywhere like a giant belt sander. Some regions may have remained frozen to the bed, with very little sliding and therefore relatively little erosion. If so, landscapes that existed before Greenland became heavily glaciated may still be preserved beneath modern ice. The new valleys could help identify where those ancient surfaces survived. That possibility changes the way Greenland should be imagined. Beneath the white surface is not simply rock polished flat by millions of years of ice. In some places, there may be river valleys, mountain slopes, and drainage networks inherited from a climate that existed before the modern ice sheet. The ice is effectively preserving a buried continent, and scientists are beginning to read it without removing the ice. This is particularly useful because Greenland's bed is almost impossible to explore directly. Drilling through kilometers of ice is technically difficult and extremely expensive. Only a handful of locations have ever been sampled directly at the bed. Most of the landscape will probably never be physically visited. Satellites and radar therefore become the only realistic way to see it at continental scale. The new map is unlikely to be the final version. Future radar surveys will reveal additional details and provide tests for features inferred from surface flow. Higher resolution satellite measurements could improve the inversion. Researchers can also combine the map with geological, magnetic, gravity, and seismic data to reconstruct both the shape and composition of Greenland beneath the ice. But even the current result changes one important assumption. The Greenland ice sheet may look smooth because ice has buried everything beneath it. The land itself is anything but smooth. There are valleys broad enough to channel enormous glaciers. There are mountains concealed beneath kilometers of ice. There are drainage networks that may have carried rivers before the Arctic looked anything like it does today, and every one of those hidden features can influence what happens as Greenland warms. When an outlet glacier retreats, it does not move across an abstract flat surface. It follows this buried terrain. A ridge may temporarily stabilize it. A deep valley may open a pathway farther inland. Old river systems may become future routes for ice flow. That is why a map of a landscape no human can see could eventually improve predictions for coastlines thousands of kilometers away. Greenland's ice tells us what the surface looks like today. The landscape underneath tells us where that ice may go next.